Okay, so let me start with the puzzle. Think about the Earth that revolves around the sun and the GPS that you probably use in your way here this morning. What is common between the two of them? Well, for starters, both of them rely on the same law of physics. So let's unpack this, starting with what even is physics? Physics is the exploration of nature's mysteries, spanning the crazy world of subatomic particles, the structure of atoms, the mechanics of flight, the orderly structure of the solar system, and even the evolution history of the universe, from the Big Bang to the present day, and ultimately to its potential sad, empty fate. Physics is the quest to understand nature and find the underlying laws that govern the universe. Understanding the laws of physics allows us to put them into use, like creating technologies, such as airplanes, trains, etc. Now, remember the two examples from the puzzle I mentioned at the beginning? Well, both of them rely on elements of a common theory, which is called general relativity. It's currently the best known theory of gravity, and it comprises the laws of physics at large scales, ranging from planetary motion, galaxies, and up to the evolution of the universe. As for small scales, there's another theory, which is called quantum physics. It explains how particles interact, and it works well down to incredibly tiny scales. Now, how tiny are we talking? Well, if you're measuring this in meters, it's 0.00019 times followed by 1, like that small. Quantum physics is crucial for many of our technologies, such as transistors, which are the building blocks of phones that you all use, for example. Now, while it's an oversimplification, you can think about the two theories, namely general relativity and quantum physics, using the following analogy. We have two doors, one labeled large scales, and the other labeled small scales. So if I want to understand and you can think about it two theories as keys to the relevant door. If I want to understand large-scale phenomena, I use the relativity key. And if I want to understand small-scale phenomena, I use the quantum key. Beyond each of the two doors are a lot more doors characterizing the different phenomena at each scale. Now, while both theories are incredibly successful, they are not complete. There remain locked doors, some from which the keys just don't work, and others that we have yet to try to open. I will only mention the ones I work on in my research. So on the keys don't work side, there's the problem of dark matter and dark energy. In brief, observations indicate that everything we can see around us and interact with, like matter, light, and planets, make up at most 5%, like only 5% of the total energy content of the universe. And we do not know much about the remaining 95%, and we call it dark matter and dark energy. On the unopened door side, there are black holes and gravitational waves, which remain largely unexplored. This is the focus of my presentation today. So what are black holes? Black holes are extreme regions where gravity is so strong that nothing, not even light, can escape. They are truly one of the most exotic predictions of general relativity and are true no-return zones. Now, in order to test whether general relativity accurately describes black holes or not, it is necessary to study how a black hole behaves. However, there are two issues with this. First is that black holes are very far away from Earth, so we cannot just go there. Second, let's imagine you could go there. Now, since you want to get close to them, you could happen to fall inside a black hole. Now, if that would happen, then of course you may discover their secrets and even write a revolutionary paper on it and try to send it to us, but we will never receive it. And your name will not go down in history. Now, here's the turning point. So, fortunately, there's another way to study black holes, or how a black hole behaves, which is through its own interaction with other objects. For example, the interaction of one black hole with another black hole. So, when two black holes get close, they start to move around each other in a spiral shape. And while they do so, they emit waves called gravitational waves, which are ripples in the fabric of space-time itself. This continues until they eventually merge into a single black hole. Now, this interaction of two black holes is called a black hole in spiral. Under the right circumstances, the emitted waves can be detected here on Earth, and they help us test general relativity under extreme conditions. Now, in order to test general relativity, it is necessary to use it to simulate how these black holes move around each other and emit the waves. However, general relativity is complicated, and so doing these simulations is very complex. And the main bottleneck of existing simulations is the lack of exact formulas, so that even using the best techniques and using the most powerful computers, it can take from months to even years to do the simulations. So this brings me to the main question of my research, which is, can we find a way to make black hole in spiral simulations more efficient? Now, in order to explain our working method for trying to answer this question, let's consider a much simpler problem, where there is no spiraling motion, away from the complications of general relativity. And the problem I want to consider instead is the motion of the Earth around the Sun. Now, let's pretend that we don't know the orbit of the Earth around the Sun, and that it's a challenging problem, and we want to simulate it. Now, this is a problem of large scales. Since we're having problems or trouble solving the problem at large scales, let's try to replace or find a similar problem at small scales. Maybe we'll have some luck there. And this is exactly the first step of our method. So, the first step, we ask, where can we find in nature a similar problem like this to this large-scale problem? Here's the Earth motion of the Earth around the Sun. Now, here we have two bodies. There is the Earth and there is the Sun. And if we want to replace the problem according to to small scales, we need to use the building blocks at small scales. And at small scales, we have subatomic particles. So let's try to replace the problem accordingly. So instead of the Sun, let's consider the much smaller and lighter proton, and instead of the Earth, the electron. Now, indeed, the proton and electron attract each other in a similar way as the Earth attracts and the Sun attract each other. Moreover, this system of the electron and a proton has a name. It's called the hydrogen atom. And now begins the second step of the method, where we solve the hydrogen atom. Now, you may be wondering, why are we able to solve the hydrogen atom when we couldn't solve the original problem? And the answer to this question is that whereas the original problem was a problem of large scales, the hydrogen atom is a problem of small scales. So we can use quantum theory or quantum physics to solve it. That's great. So, assuming we solve the hydrogen atom, we now ask, can we somehow translate the solution of the small-scale problem into a solution of the large-scale problem? Here is the motion of the Earth around the Sun. And here is another turning point. We found in our research that the answer to this question is also yes. So we can find it this way and obtain a solution to the large-scale problem. Hence begins the final step of our method, where we translate the solution of the small-scale problem into a solution of the large-scale problem. Here again, it's the motion of the Earth around the Sun. Okay, that's great. So if we go back to the analogy from the doors analogy from before. So if before we needed to use the relativity key to open the large scales door, we now do a trick. We use the quantum key, and by means of translating the problem back and forth between large scales and small scales, we're able to use it to open the large scales door. And if I now go back to black holes, which we started with, we do a very similar approach. We again use the quantum key or quantum physics to try to unlock the unopened doors of black hole in spirals. Now here is some exciting news. So in about 10 years, a space-based detector will enable us to compare the simulations with the real data. Now you might be thinking that 10 years is a long time, and even wondering that how different your lives will be by then. But remember that 10 years is a very short time when compared with the evolution timescale of the universe. The collected data will offer a crucial test of general relativity, and upon comparing our simulations with the collected data, we'll find out if the data agrees with our simulations or not. If they do, then we'll know that general relativity works well for black hole in spirals. And if they don't, then that's even better, because this will point us to a deeper theory of gravity. Thank you for listening.